Eason, do you remember what number it was or what it was asking?
It was the one that had like something like B equals P plus N.
So that one's a dot product. That one is just graphing and finding the angle. Graphing and finding the angle.
Parallel and
Dot product. Dot product. Projection. Projection. Work. U equals P plus N. All right, it says for the vectors U equals 3, 2, and V equals negative 3, 1, express U as the sum U equals P plus N, where U is parallel to V and N is orthogonal to V. This is pretty much a projection problem. So we want to break apart U into two pieces. One of them is going to be in the same direction as V. So we want to project U onto V. And then we want the orthogonal projection. So back when we first started projections, we said we can break it apart into two pieces. And we called it W sub 1 and W sub 2. So we said to find W sub 2, which is the orthogonal one, all you have to do is subtract. So the one that's in the same direction is the projection, and the one that's orthogonal, we'll just subtract to find that one. Okay, so we'll do this problem. So U is 3, 2, and V is negative 3, 1. We want U equal to P plus N, where P is parallel to V. N is orthogonal to V. So the parallel piece is the projection of U onto V. This is going to be P. Does anybody remember the projection formula? U onto V.
It's like, I know it's something over the magnitude of U squared?
Nope.
Or V squared?
V squared. So we're going to have magnitude of V squared in the bottom.
Is it the dot product on top?
Dot product on top.
Times
Multiplied by V on the outside, because that's the direction we want our new answer to go in. Yep. So dot product in the top, so 3 times negative 3 is negative 9. And then 2 times 1 is 2. The magnitude of V is radical 10. And we're going to square it, so it's just going to be regular 10. And that's going to give us a coefficient to multiply through into V. So negative 9 plus 2 is negative 7. So we've got negative 7/10 that we're going to multiply in to V. So negative 7/10 times negative 3 is going to be 21/10. Negative 7/10 times 1 is negative 7/10.
Alright, so in this answer, how do you know which goes first?
What do you mean?
It got to a point where I was getting the answer right, but then I would have it in the wrong box. When I put the answer in.
So, okay, it says P is parallel, and it says write it as U equals P plus N. So they want the parallel one first, and N is orthogonal, and they want that one second. So do the parallel one first, and that one is the projection. So do the projection first, and then do the other one second. So you got to be very, very careful about exactly how they worded it. So do the projection first. So U equals P plus N. We know U, and we know P, so we can get N with subtraction. If U equals P plus N, then N equals U minus P. Just algebra. Minus the N, or minus the P over to the other side. So N is going to be equal to our U, which is 3, 2, minus the P we just found, which is 21/10, negative 7/10. So 3 is the same as 30 over 10. So 30 minus 21 is 9. And then 2 is the same as 20 over 10, and we're subtracting negative 7. So we're really adding 7. So 27 over 10. So the P is the projection, and the N we get just by subtracting. Okay?
I figured out how to get the answer, but I didn't know why.
Mm-hmm. To know exactly what you were doing and why you were doing it, like a trained monkey. Yeah, so that is problem number 10 on the homework. So we're taking a vector and we're breaking it apart in two pieces that are 90 degrees apart. They give us the direction for one of the vectors, and they want the other one to be perpendicular. They never say projection, but that's exactly what we talked about when we described projections. So that's how I knew to do projection. And then 11 is a cross product, 12 is a cross product. 13 says find a vector normal to the two given vectors. So what do we do? Cross product. 14 says compute the magnitude of U cross V. If the magnitude of U is 8 and the magnitude of V is 2 and the angle between them is 5 pi over 6. So we have a formula back in our geometric properties of cross product that will help us figure this out. It says compute the magnitude of the cross product. So we've got a geometric formula that says sine theta equals, or that
Magnitude of the cross product.
over, yeah, sine theta equals magnitude of the cross product over the magnitude of the individuals. Yeah, so you could use that formula to figure out that answer. Cross product, but it just says negative k cross negative I. So those are standard unit vectors. You might want to write them out as like the 1, 0, 0, 0, 1, 0. Write them out in component form, and it might make a little bit more sense. Uh, 16 says find the area of the parallelogram. Area of a parallelogram is magnitude of a cross product between those two vectors. And then the last one talks about torque. And we did an example of torque right at the end of our cross product section. And that's the cross product between the vector that represents the lever and the vector that represents the force being applied to it. So we've got a lever that's at an angle, and we have a force being applied to it. So we want to write those both out in vector form and then do a cross product between them. What we're going to talk about today is lines and planes in space, which is actually a pretty interesting section. We're actually going to start doing something with these dot products and these cross products besides just kind of random calculations. We've just been doing a lot of algebra, a little bit of trigonometry. Haven't really done a whole lot of applications with it yet. We'll actually start doing, it's still not a whole lot of applications, but we'll see actually some geometry that's associated with these dot products and these cross products, and start to see some things that they can be used for. So this section is broken almost perfectly in half into lines and then planes. A whole bunch of stuff with lines and then a whole bunch of stuff with planes. So we'll try to get through lines here in the first half, and then we'll come back after break and do planes. So lines in space are very different than lines in the plane. In the plane, we write a line with just an X and a Y with powers of 1. There's a couple of different formats we use. There's a standard form, there's a slope-intercept form, there's a point-slope form. This one is usually called standard form. But since there's only 2 variables, we can represent the change in one by the change in the other, all just in one equation. In space, we can't do that because there are 3 variables, and they can all change independently and still form a line. The slope in the x direction could be completely different than the slope in the y direction and the slope in the z direction, and it could still be a line. So when we write lines in space, we use parametric equations or we use vectors. But the one thing that is going to stay the same is that they are linear equations, and they're all tied together with a parameter, which is another variable that makes sure that they all change at the same rate, and the parameter is going to be t. So there are two things that we need in order to write a set of parametric equations of a line in space. We need a point that the line goes through, and we need a vector that points in the same direction as that line. So that point, I'm going to call it x sub 0, y sub 0, z sub 0. And that vector, I'm going to say it's vector v, and it has components a, b, c. We call this vector the direction vector. And we call these components our direction numbers. They describe the slope in each of our different directions. In the x direction, our x values are changing by about a rate of a. In the y direction, our values are changing at a rate of b. In the z direction, our values are changing at a rate of c. So as long as we know a single point on the line and a vector that points in the same direction as the line, so a line in space goes forever in both directions. So it doesn't matter which direction the vector is pointing in. It could be pointing, you could say up or down or to the left or to the right. It could be either one of the directions. We could set up parametric equations for this line. And I'm going to show you, what the vector format would look like and what the parametric equations would look like. So for the parametric equations, we're going to want individual equations for x, y, and z because they're all changing differently. They're all starting at a different value and then they're all changing differently. So we need different equations for each of them. So x is starting at x sub 0, and I know it's changing at a rate of a. So a times t. Y is starting at y sub 0, and it's changing at a rate of b. So b times t. And then z starts at z sub 0, and it's changing at a rate of c. This is a set of parametric equations for line and space. And they all have that parameter t, which they have in common and make sure that they all change at the same rate. So if I'm going to plug t equals 5 into one of them, I would have to plug t equals 5 into all of them so that they're all moving together. And that's what ensures that we stay on the same line. So we could write it as 3 separate equations that kind of get bundled together, or we could also write it as a vector. So we could also say that this line is the vector, and we would put the x equation as our x component, and the y equation as our y component, and the z equation as our z component. And this is where we start seeing variables in our components. So x sub 0 plus at, y sub 0 plus bt, z sub 0 plus ct. Either one of these is perfectly fine. It's just 2 different ways to represent the line. You might be asked for parametric equations, or you might be asked for a vector representation. Just 2 different ways to write it. There's also something called symmetric equations. And in symmetric equations, all you have to do is go through and solve each of your parametric equations for t, and then set them equal to each other. So symmetric equations for that exact same line with our arbitrary variables. If I solve that x equation for t, what is it going to look like? We've got x equals x sub 0 plus at.
X minus x sub 0 divided by.
X minus x sub 0 divided by a. And if I solve my y equation for t, what's it going to look like? Same, except you're going to have the y coordinate and the y change value. And all those t's are exactly the same t, which means all these equations are going to be equal to each other. They should all be equal to each other. So x minus x sub 0 over a is equal to y minus y sub 0 over b, which is equal to z minus z sub 0 over c. That is called symmetric equations. It's not my favorite. But just in case you ever see it anywhere. The parametric equations and the vector format are much more common, much more useful. But the symmetric equations exist. It's not something different and new that you need to memorize. It's very easy to get if you know the parametric. Just solve them for t. All right, so let's try a couple of these. Oh, hold on, let me add one more thing before, I'm gonna let you guys figure this out for yourself.
Oh, God.
No, it's not a bad thing. It's not a hard thing either.
You're recording, right?
I am.
Okay. Make sure.
Oh, am I? I don't see the record thing.
It's a 3, 2, 1. Yeah, it says
Oh, yeah.
recorder is recording.
Good.
That's something I can hear us to play.
All right, so this first one, we're going to find a set of parametric equations. This one's just going to be very easy and basic. Find a set of parametric equations for the line that passes through the point (5, 2, -1) and is parallel to the vector v equals I minus j plus 3k. We want our answer to be parametric equations. So this one is the most basic, the most straightforward. They give us exactly what we need. We just have to know how to pull the information out and set up the answer. The vector tells us the direction numbers for each of our variables. And then the point gives us a starting spot for each of the variables.
Freaking Texas. Yeah, it's almost like Moore's Sprinkle, so we should go. We can only grill on that. Like, you know,
Just answer. Oh, that's all.
Do you know a different language?
Tiếng Anh don't. Tiếng Trung.
Answer it. Answer in a different language.
Oh, there's one where like they do some telemarketer and calls a crime scene and the cops is messing with it and it goes on for like 5 or 6 minutes. It's really funny.
Sir, you just called it an crime scene where I want to interrogate you, ask you questions of why you calling him and I saw.
All right, to write parametric equations, each variable needs a spot to start from, and then it needs to be told how to move from that spot, how many units to move at a time. And since it's a straight line, it's got to be consistent in how many units it moves every time. If it moves a different number of units every time, it's not going to be a straight line. So straight lines, remember, have constant slopes. When you start having a variable slope, that's when you start having the curves. Curves have variable slopes. That's when we learn derivatives. And we start having variables in Calculus 1, when we did derivatives for tangent lines and things like that. So for x, what can we use as a starting point? No. 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 5. We know this line goes through the point 5 to -1. So I know at some point in time, x is going to be equal to 5. And then I know at the exact same point in time, y is going to be 2 and z is going to be -1. And then as we move away from that point, we need to make sure that the x is moving in a certain number of increments, the y is moving a certain number of increments, the z is moving a certain number of increments, so that it's parallel to this vector. So we want to use those direction numbers. And those are going to be the coefficients on our t's. It tells us how to change the x-coordinate, the y-coordinate, and the z-coordinate every time we want to move to a different point on the line. So the x-coordinate is going to change by how many every time? Just one, because we've got a little imaginary 1 there in front of our eye. And you don't have to write a coefficient of 1 if you don't want to. And how much is the y going to change by every single time? -1. So we can write that as minus t. And then the z? Huh? 3. Yep, so plus 3t. That's it. So the coordinates from the point make up our constants. The components from the vector make up the coefficients on the t. And that is the set of parametric equations for our line in space. So everybody should have gotten the same answer for that one. For our next example, it's a little bit different. We're going to find a vector representation. And all that means is we're not going to write it out as x equals y equals z equals. We're going to take those and we're going to put them in the x, y, z spots in a vector. So we did write that down a couple minutes ago. For the line in space that passes through the points (1, -3, 9) and 3, 0, 5. What two things do we need to write the equation of a line?
Any one point, any set of points.
We need a point on the line.
We use any of those, right?
We could use either one. Yep, we need a point on the line, and we need a vector that's in the same direction as the line. So we need a vector. They didn't give us a vector. They did not give us a vector. They gave us 2 points on the line. It doesn't have to be a unit vector. It could be, but that's going to be an extra step of work that you didn't have to do. Because the line has an infinite length. It goes forever in both directions. So it really doesn't matter what the length of the vector is that we use. But we have to make a vector. What do we need to make a vector? Arrows.
Magnitude and direction.
Either a magnitude and a direction, or what we do in our project. Step number 1 of our project. How did we get component form for our vectors? The one I handed you back at the beginning of class. What information did I give you and ask you to find component form for vectors?
What was your question? I'm lost. What information did you?
What information do you need to create a vector?
What's that? Just
2 points.
Yeah.
So either magnitude and direction or 2 points.
So 2, 3,
So we can, even though they didn't give us a vector, we can write a vector.
2, 3, 4.
So this is where I said earlier I was going to let you guys figure it out for yourself. Adam, why did you do the second point minus the first point? Just out of habit, right? This, because we're doing this for a line, and the line goes forever in both directions, there's not really a specific starting and ending. It could have gone either direction.
Yeah.
So we could have done the first minus the second, or the second minus the first. So either one of them would have been correct. What happens if you change the order of the subtraction? All the signs are going to be opposites, right? So you'll get a different answer. But it would still be correct. It would still be the same line, and it would still be correct, but your answer would look different. So these answers for these equations in space, they are not unique. Several people can get several different answers, but they are all correct. I can mathematically show you how you're each correct, though. It's not, it wouldn't be my opinion. So 2, 3, -4 would be a vector for this line, but also -2, -3, +4 would work, because a line points forever in both directions, and a vector only points in one direction. So 2, 3, -4 would work for one side, -2, -3, +4 would work for the other side. So either one of them is perfectly fine. The other way that we could get a different answer is, now that we have a vector, we're ready to set up our answer. So we need a point and a vector to set up the answer. Which point do we use? You want to use the first one? Why? Because it's first? Doesn't matter. You can use either one. It doesn't matter. So if Ethan uses the first one, he's going to get a different answer than Adam, because Adam wants to use the second one. So there's actually, for this one, there are 4 obvious different answers that we could get if you do your subtraction differently when you set up your vector, and then if you use a different point when you set up your equations. There's already 4 different answers you could get that are all correct. Oh yeah, there's an infinite number of possibilities, because there's an infinite number of points on that line. Any one of those points could be used to set up that vector. And then any vector that's parallel to that could be used as the direction vector. And there's an infinite number of vectors that are parallel to that. I say there's 4 obvious ones just because of the information we have given to us right now, without going above and beyond and creating more work for ourselves. Just from what I have right now, there's 4 obvious ones. So from the direction numbers we have and the points that we're given, I'm going to write out all 4 of the possibilities. You would not ever have to do that. As long as you can come up with one of them, then you got it. But just in case you did, a bonus question for all 4. But just in case you did it differently, or you used a different point, or you did your subtraction differently for your vector, I just want you to see that you could have a different answer. So for the x, if we used the first point, it would be 1 plus 2t, -3 plus 3t, 9 minus 4t. That's if I use the first point. If I use the second point, this is the exact same line. It would be 3 plus 2t. 0 plus 3t is just 3t. And then 5 minus 4t. That is the exact same line. You would eventually, If you plug in different values for t, you would eventually come up with the exact same set of points. Now, if we turned around the subtraction in our vector, it would change all of the signs on our direction numbers. So we also could have 1 minus 2t, negative 3 minus 3t, and 9 plus 4t. If we had done our subtraction in our vector opposite. We also could have had 3 minus 2t, negative 3t, or 5 plus 4t. Any one of those four answers you could have gotten from the information they gave us, depending on how you subtracted to get your vector, and then depending on which point you used to set up your answer. So the moral of the story is that the equation or the equations, the vector equation for a line in space is not unique. There are an infinite number of representations for the same exact line in space. Questions so far? Last question before break. Wild guess?
No, yes.
We got a no and a yes.
Any other guesses? Take a smart box.
Does anybody have any reasoning behind their guesses? Is the point 8, negative 2, 5 on the line represented by the vector 4 minus 2t, 1 plus 3t, 2 plus t? Got another no. Got somebody change. Somebody changed to no.
I was joking, I really don't think so.
If there were on the line.
Can you scroll up real quick? See all the four? No, keep going.
Okay.
I just want to see. the other.
So most of the time in parametric equations, people think of t as representing time. It doesn't have to, but people think of t as representing time. It can represent tangerines. That's a lot more fun.
So it's like
When will x equal 8? When t equals -2. So I'm going to set them equal to each other and see what's going on. Remember, these things need to move together. The x, the y, the z need to move together. So if x will be 8 when t is -2, then y needs to be -2 at t equals -2. And z needs to be 5 when t equals -2. So once you solve for one of them, you can take it and you can check the others and see if it's true. And it's not. So 1 plus 3 times -2. Y is going to be at -5. And then 2 plus -2, z is going to be at 0. So nope. 8, -2, 5 is not on that line. When x is 8, the y and the z are not matching up. And you don't necessarily have to solve for the x. I did the x just because I saw an easy way to solve for it, because I saw all those even numbers and I knew it would work out even. If you see a different one's going to work out easier, you just have to solve one of them for t and then check the other ones. All right, we're going to have a break, and when we come back, we're going to talk about planes.
That lab, number 19, what was the
back here today.
I don't know if they can hear you. When I listen to the videos, I can't ever hear you guys' voices.
And we're back here today with Calculus 3.
Now we're making rocket engines.
Nice picture of the moon right here. I think it's time for potty research.
Do what?
What? He's gonna launch porta potties. That's what we're doing yesterday.
You can't even do a PVC pipe 3 feet.
No, it's a game.
Oh.
You know it's a misdemeanor if they catch you doing if you get on the phone now.
I still have to go to a movie tonight. Go watch a movie.
What movie?
I guess I'm gonna go see Split.
I heard it's really good.
Yeah, I'm not tired. I'm gonna go to sleep.
I went and saw the Batman Lego movie.
Oh my gosh, I'm not going to do that.
My favorite part of the whole movie
What's
is
the end?
when they're no, listen, it's not a spoiler. Well, it kind of is. So they're in a gunfight, and the little Lego guys are actually saying pew 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 pew. I loved it.
The only reason I wanted to see it.
So what happens if one of them gets shot and it's like their chest can fly?
It's a kids movie. Nobody gets shot,
Uh,
but they're just saying pew 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 pew.
Maybe I'll go see 50 Shades.
No.
Why not?
I saw the first one.
wants to see that movie.
You want to see it?
She wants to see the 50 Shades of Grey. She wants me to buy it.
So, like, I was looking for this card last night for Valentine's Day, and I didn't want to be all sappy, because I hate that. And I wanted to be funny. And it took me like 20 minutes, but I found one with Snoopy, and he's in a plane. And I was like, that's perfect. But I was like, why is that perfect? Does she like airplanes? I was like, I don't know, but I do. I think it's
So it's technically a spaceship.
Oh, I did find You did do pandemic? Oh, I could play that.
Yeah, I actually killed everybody.
I played a hack game.
I think I played on the relaxed version though.
All right, to write the equation of a plane in space, and this one's actually going to be one equation that has the x, the y, the z in it. This is the most basic equation that has the x, y, z all together. So in the plane, the most basic equation that has the x and the y together is the equation for a line. The most basic equation in space that has x, y, z together is the plane. In order to write the equation for a plane in space, we need a point in the plane, which we're calling P, which has coordinates x sub 1, y sub 1, z sub 1, and we need a vector that is normal to the plane. We can't just have a vector that is in the plane because that only represents one direction. And technically, a plane has two directions. If you think of the xy plane, the x, what's the word I'm thinking? The x-axis is one of the directions and the y-axis is one of the directions. So a plane always actually has two directions in it. So we can't just have a vector in the plane, we need a vector normal to the plane. So a vector that is normal to the plane could technically come about from a cross product between two vectors in the plane. So two vectors in the plane, if we crossed them, would give us a vector normal to the plane. And we can use that one vector that's normal to the plane to represent the plane. The point in the plane and the vector normal to the plane. So the technical definition for the equation of the plane is the dot product between the normal vector and the vector PQ, wherever that is equal to 0. When is a dot product equal to 0? When it's 90 degrees, right? So I want this dot product to equal 0. So I know that my normal vector should always be normal to the plane, which means this PQ vector should always be in the plane if it's going to be normal. I know P is in the plane, which means this vector Q should always be in the plane. And we're going to let Q be arbitrary. Q is just our arbitrary XYZ. So the plane is represented by the dot product between the normal plane and the vector PQ, where Q is an arbitrary XYZ and P is a point in the plane. Every time that dot product comes out to be 0, we have the equation for our plane. So what this looks like, and you don't have to work this out every time, this is going to lead to an easier formula that we can actually do. Vector PQ, we're going to do the Q's minus the P's. So this is going to be X minus X1. Y minus Y1. Z minus Z1. And then when we dot that with n, remember we multiply corresponding components. And n is our direction numbers that are normal to the vector, a, b, and c. So this is going to be a times x minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. This is called standard form for the vector, or for the plane. This is standard form for the equation of the plane. So we see those direction numbers, A, B, and C from the normal vector, and we see the coordinates x1, y1, z1 from the point. But if we want to, there's a little bit of algebra we can do. We can distribute the A, the B, the C, and that will give us some like terms to combine. So really, if we want to clean this up a little bit, we could write this as AX plus BY plus CZ equals D. Because A times X sub 1 is going to be a constant, B times Y sub 1 is going to be a constant, C times Z sub 1 is going to be a constant, and we could combine them all together and move them to the other side. That is called the general form for the equation of a plane. And don't think of it as two different formats that you have to remember. The way that we get the second one is just by continuing to simplify the first one. So we're going to find the general form for the equation of the plane containing the point 0, 5, negative 2 that is normal to the vector one, 1, 3. So there's not much work to do on this one. This is just to get us familiar with the format and what to do with our different numbers, where each of them goes, what the setup is. And then we'll work our way up to some more difficult problems. So 0, 5, negative 2 is in the plane. And if you want to think of it this way, any other random point Q that's also in the plane we can create a vector between P and Q, and that vector will always be in the plane. So if we do a dot product between this vector that's in the plane and the normal vector, they will always be 90 degrees apart. So that dot product will always be 0. So 1 times x plus 1 times y minus 5 plus 3 times z plus 2 will always equal 0. This is the standard form. You don't have to set it up like the dot product. you can just remember the standard form we have up here, where you do A times X minus your X coordinate, B times Y minus your Y coordinate, C times Z minus your Z coordinate. But that's where it comes from. If you take your point and then just any other random point, which we represent as X, Y, Z, and we create a vector out of them, and we say that is any vector in the plane, and we dot it with the normal vector, it's always going to have a dot product of 0, because they'll always be 90 degrees apart. That is standard form. Just leave it like that is standard form. We want general form, which means we want to do some simplification on that. So 1 times X is just X. 1 times Y minus 5 is just Y minus 5. And then we can distribute the 3 and the Z plus 2. So we get plus 3Z plus 6. And we've got some constants we can put together. We've got a minus 5 and a plus 6. And then we also want to move it to the other side of the equation. It's going to move to the other side as a negative 1. So on the left, it's a positive 1. It's going to move to the other side as a negative 1. So it's X plus Y plus 3Z equals negative 1. What were the components for the normal vector? One, 1, 3. What are the coefficients on X, Y, Z? So even after we do the algebra to get it into general form, you can still see those components. The 1, 1, 3, we still see them here. So you can still look at the equation for a plane and look at the coefficients and figure out what the normal vector is. What we can't see is what point got used. Because we distributed and combined, we can't see the point anymore, but we can still see the normal vector because it's the coefficients. Okay, so that's the equation for our plane. X plus Y plus 3Z equals negative 1. We're going to find the general form of the equation of the plane that contains the point negative 2, 1, 7. And the vectors R equals 102 and S equals negative 213. We want the plane that contains all that stuff, that point and those two vectors. What sort of information do we need to start writing the equation for a plane? There's two things that we need. A point and what kind of vector? We need a point and a normal vector. What does normal mean? There's two other synonyms for normal that we keep using. Orthogonal and what's the old-fashioned word that we learned in perpendicular? Perpendicular. So we need a point and we need a normal vector. They gave us a point, they did not give us a normal vector. They gave us two vectors that are in the plane. How can we find a normal vector? We're not going to do standard position. We would need 2 points to do standard position. Cross product will give us a normal vector. The cross product of 2 vectors gives a normal vector. Cross product of 2 vectors is a normal vector. And if those 2 vectors are in the plane, the cross product will be normal to the plane. So we want to do R cross S or S cross R. Either one, doesn't matter. So R is 102, S is negative 213. So for the I's, I'm going to do 0 minus 2. So I've got negative 2I. For my J's, I'm going to do 3 minus negative 2, which is really 3 plus 2, or excuse me, 3 minus negative 4, which is 3 plus 4, which is 7. And the J's change sign, so this is minus 7J. And then for the K, I've got 1 minus 0, so plus K. The equation for a plane is unique. So if you did S cross R, cross product is not commutative. If you did S cross R, you would get a different vector. You would get positive 2I plus 7J minus K. But your equation, your final equation for your plane would be equivalent. If you use a different point, if you had multiple points to choose from when you set up your plane, your final answer would still come out the same when you set up the equation for your plane. So you won't get multiple answers that are all correct when you set up the equation for a plane. There's only one answer. So I'm not going to set up all that dot product stuff. I'm going to go straight to the format. So those direction numbers give me my coefficients. And inside the parentheses, I'm going to do the variable minus the point. So the direction number for x is negative 2. And then x minus our x coordinate, which is negative 2. So x minus a negative 2. The direction number for y is a negative 1. And then y minus your y coordinate, which was 1. And then the direction number for z is 1 times z minus your z coordinate, which is 7. So the numbers in front are the components from the vector. The numbers inside, we're subtracting the coordinates from the point. So the components from the vector were negative 2, negative 1, 1. Negative 2, oh, whoops, that's negative 7, sorry. Negative 7, 1. Negative 2, negative 7, 1. Negative 2, negative 7, 1. Sorry about that. And then the coordinates from the point were -2, 1, 7. -2, 1, 7. And we need to simplify this because we want the general form. So that's really x plus 2. And if we distribute, we get -2x minus 4 minus 7y plus 7 plus z minus 7 equals 0. We're not going to do this problem, but I want us to brainstorm for just a second. And then we're going to go on to distance, just so I can make sure we finish this section today. How would you find the equation of a plane if I gave you 3 points? So think about what you need and how we can get there. Triple scalar is going to give it's going to give a volume. Triple scalar is going to give a volume. But you're on the right track. You're on the right track. The answer to a triple scalar is just a scalar.
The opposite.
We're going to have to do a cross product. We can't plug points into a cross product. Vectors go into a cross product. We're going to make 2 vectors. And then we're going to find their cross product. That's going to give us a normal vector. So if you're given 3 points, you're going to use those 3 points to make 2 different vectors. And then you're going to do the cross product of those 2 vectors. That will give you a normal vector. At that point, you'll have a normal vector, and then you'll have 3 different points to choose from. And what do we need to set up the equation for the plane? A normal vector and a point. So we're ready to go. Yep, so all you have to do is use those 3 points to set up 2 vectors, and then do the cross product of those 2 vectors, and you've got your normal vector. All right, the last thing we need to talk about is distance. And the formula you're going to see is actually going to be something we've already used before. It's just kind of in a different context of what we've done. And there's 2 different distances we're going to talk about. We're going to talk about the distance between a point and a plane, and the distance between a point and a line. So if I want to know how far apart the point and the plane are, what's the shortest distance between the point and the plane? So there's an old saying about the shortest distance between 2 points, right? The shortest distance between 2 points is a straight line, right? The shortest distance between 2 objects in space is always going to be the perpendicular distance. Technically, I can connect that point to the plane anywhere on the plane, and all of the distances would be different. We're just looking for one answer, and we want the answer to be consistent with everybody. So the shortest distance is technically what we're looking for, and the shortest distance is going to be the distance that is perpendicular to the plane. So we're going to go straight down, perpendicular.
So we no longer have a 3D plane?
It is a 3D plane.
Oh, okay, I got you.
It is a 3D plane.
So dripping out from the Z coordinate.
Yeah, but it could be slanted. It could be a slanted plane, but we always want to connect our point perpendicular to wherever the plane is. We always want to connect our point perpendicular to it. No, a plane goes on forever in every direction, kind of like a line does. So the distance always refers to shortest distance. Which is perpendicular. Which is actually going to be really easy to find, because we already know, if we know the equation for that plane, then we know the normal vector. So I already know what direction that is. All we have to do, so let's call this point P. And if I know the equation for the plane, what we're going to do is we're going to find a point that's in the plane, point Q. And we are going to create vector PQ. And we are going to project it onto the normal vector. And we just want to know how long the projection is. So that distance is the projection of PQ onto N. Just the length. And there was a different name for just the length of the projection. We called it something else. It had an S in it. The scalar. The scalar projection. And it allowed us to simplify the formula and eliminate some of the pieces of the formula. We still want to do absolute value though, since it's a distance. We don't care about it coming out negative. So we're still going to keep absolute values around it. We just talked about the projection formula at the beginning of class when we reviewed that homework problem. Okay? The scalar projection left off the piece that turned our vector into a unit vector. Okay? So what was the numerator? So remember what the numerator was in that?
Oh, it's
Just about to say, is the dot product. So this is going to be PQ dot N. And what was in the denominator?
Just magnitude.
Magnitude of which one?
V.
V, which is the one we were going on to. So here it's going to be N. It's always the one you're going on to. That's going to be the distance between P and the plane.
So it's just pretty much the general form. The kind of
So the normal vector N is where comes from the plane. And even if it's in general form, we can still pull those numbers out from the coefficients. P would be given to us. Now Q, we're going to have to get that ourselves from the plane. And I'll show you how we can do that pretty easily. We just need to figure out any point at all, any point whatsoever that's in the plane. And there's an infinite number of points in the plane. We just need to figure out one of them. So we are going to find the distance between the point 5, 2, negative 4 and the plane 2x plus 3 minus 3y plus z equals 9. Which means I'm going to connect 5, 2, negative 4 to the plane with a vector, and then I'm going to project that vector onto the normal vector and see how long the projection is. It's basically what I'm doing. So this is P. What they gave me is P. It's a point off the plane. We need to find a point on the plane, and we also need to identify the normal vector. Those are the three main pieces we need to do this problem. What is the normal vector? 2, negative 3, 1. Does everybody see where we got that from? It is the coefficients in the equation for the plane. We said even if the plane is in general form, we will still see those direction numbers as coefficients. So the normal vector is the coefficients, 2, negative 3, 1. And then we need a point that's in the plane, and it can be any point. So what we can do, there are an infinite number of points in this plane. You pick an x value and a y value, any x and y that you want, and you plug them in and solve for the z that goes with them. And I'm going to do something really simple. I'm going to pick x and y equals 0. If x and y equals 0 in that plane, what's z? Nope. In the plane, if x and y are 0, what are we left with? If x and y are 0, what does it say?
Oh.
Z equals 9. Z equals 9. So to find a point in the plane, you're going to plug in 2 of the values and then solve for the third. So I'm going to use 0, 0, 9 for my Q. You could plug in 0 for X and 0 for Z, and then use negative 3 for Y. And that's perfectly fine. You'll get a different PQ vector, and your PQ dot N should still come out the same though. The combination still should come out the same.
Now we have to do a PQ, right?
Yes. Now we have to create the PQ vector. We've got a point off of the plane and we've got a point on the plane. We need to connect our point to the plane. Really doesn't matter what direction it's pointing in, because at the end we're going to absolute value it. So 0 minus 5 is negative 5, 0 minus 2 is negative 2, 9 minus negative 4 is really 9 plus 4, which is 13. So this is how we get our point to the plane. But we need to get it there perfectly perpendicularly. This is going slanted. So I don't want the magnitude of this vector because this is going sideways. And that's not the most efficient way. So that distance is not helpful. Because if somebody connected P to a different spot, they'd have a different answer. So now we want to project this onto the normal vector to get the shortest distance so that we all have the same answer. And we only want to know how long it is. We don't want to actually know what the vector is. We just want to know how long that is. So it's really a scalar projection. So we want the absolute value of PQ dot n over the magnitude of n. We might not need the absolute value, but just in case, because sometimes these come out negative. So PQ dot n, we've got negative 5 times 2, negative 2 times negative 3, and then 13 times 1. over the magnitude of n. Oh.
So.
Hmm.
Since my point would be Q, how'd you get? Hold on, scroll
Yes.
up. Oh, wow. Gotcha.
2.41.
Mhm. So distance is a scale.
Mm-hmm.
And what would it be asking if we were to pop up another vector?
If we were to find another vector, what do you mean?
Like if we were to do the, let's say, just a projection. Instead of a straight projection. Like if we multiply, rather than that, and then multiply by. Normal vector.
It would probably say find the vector projection or project onto the normal vector. But anytime you see a problem that asks for distance, it's going to be the scalar projection. So the distance is just like taking out a ruler and seeing how far. So this is about 2.5 units away. The point's about 2.5 units away from the closest spot on the plane. There's one more real fast, then we're gonna go. Okay? I know we're dying. We don't have class Thursday. Did you find your problem?
Yeah.
Okay.
So the test is going to be online or?
Yes, I don't have it finished yet.
Okay.
I was trying to grade the projects. I got Adams done, and then I found some things on the Easons and Kirby's that I wanted them to fix that I know they didn't do on purpose. So I gave theirs back, and then I didn't get to yours and Tyler's. And then I didn't get, because I was doing that for the hour right before class, and then I didn't get a chance to do the test. But I already have like 5 old tests, and I'm probably just going to tweak them a little bit. So it's not like I'm making it from scratch.
Which one's right?
It's not multiple choice.
How many questions are wrong? It's matching?
It's not matching. It's probably about 15.
Crossword thing? What? What was it?
How many questions on the test? How many questions on the test?
We got it. 405,
I am gonna put some 11.5 homework. Not a lot, but I want you to, if you get stuck on the test, I want you to have maybe something to go reference or something to practice in case you get stuck on anything. I want to show you really quickly the distance between a point and a line. Okay, the formula is just a tiny bit different. And the reason is because when we don't have We don't have a normal vector when we have the equation for a line. So it's just a tiny bit different. Let me show you that real fast, and then we'll go.
How soon are these notes are gonna be, how soon are you posting notes?
Usually within just a couple hours. The notes and the video are on our Moodle page.
Is there like a way of
Yeah. Yeah, it's a PDF file. All of the notes that I've done like this are uploaded as PDF files on our Moodle page. And the videos are uploaded to YouTube, and the link for the YouTube videos up there.
are you
Huh? Am I YouTube famous? I do have one trig video that has over 2,000 views.
What's your channel?
Almost all my videos are unpublished. That's the school's rule.
Oh, really?
hmm
How do you get-
Because they only want people who are paying tuition to watch them. That was before they made those rules, and I was making videos on my own because I was a wonderful teacher. It's just Shiloh Lawrence.
Oh, I was watching.
just make a website, charge
They're not that great. Did you just say I know?
I said they're not that bad.
Oh. All right, really fast because it's time to go. The distance between the point P turn that off. No, don't turn it up. Turn it off, turn it off. No, I can't stand listening to my own voice.
10 out of 10.
I know you hear that, like, do I really sound like
I'm
that?
gonna do that just because you gave me 99 on that project.
Oops. So we've got a point in space and we've got a line in space. And the line is represented, it could be either parametric equations, or we could take those equations and write them as the components of a vector function. Write them in vector format. Again, distance is going to be perpendicular distance, because I can connect that point anywhere on the line and have all sorts of different distances. But we want everybody to have the same answer, so we're gonna come in perpendicular, which is the shortest distance, so that everybody gets the exact same answer. Huh?
2,191 views.
On that trig video?
Trick values of special.
I need to redo it and make, I mean, it's not even that good. Stop.
So that's your intro. Your intro is, hi guys.
You change it. Hey, everybody.
So
Yeah, like,
embarrassing.
what is going on, guys? Shiloh Lawrence here.
So
Back at it with another
embarrassing.
video.
Today we're playing Grand Theft Auto 5.
That was so embarrassing.
It's okay. My friend, his YouTube channel it had like 100,000 views. Yeah, I think one of them. He's like, "What is going on, guys? Fleet Base COC Gaming here." And I just say that randomly all the time.
Felipe sees
Clash of Clans.
All right, really quick so we can go, because it's already like 3:18. All right, the problem with the lines is that we still need to connect P to our line. So we're gonna find a point on the line, the same way we found a point on our plane, and we're going to connect the point to the line. So we're still going to create PQ, just like we did with the plane. But we don't have a normal vector to the line right now. When we have parametric equations for the line, what we have is a vector that's in the same direction as the line. So we can't just take vector PQ and project it onto the normal vector, the same way we did with the plane. So what we do instead is we're going to do a cross product with the direction vector. A cross product with the direction vector will be normal. So PQ is here, this line is here, and then the normal vector, if you think of them as both being flat on the board, the normal vector is going to come straight out at us, which is normal to that line. So PQ crossed with the direction vector for that line. V is the direction vector for the line. So V is ABC. But what is the answer to a cross product? What type of answer do we get back to a cross product? It's a vector, right? And with distance, we're looking for a scalar. So once we get this vector back, we need to know just what the magnitude of it is. What the magnitude of that cross product. And then we're going to divide it by the magnitude of V. Which again is the direction vector for the line. We're going to have to come up with Q on our own, and we can do that just by plugging any t value into our set of parametric equations. And that'll get us a point on the line. Or we can just pull out x sub 0, y sub 0, z sub 0. That's what, that would be a point on the line when t is 0. So we're going to do one of these real fast, then we're going to go, because we are way out of time.
We can start earlier. I think we should get away from this.
Ooh. We are going to find the distance between the point -4, 2, 1. And the line L that has parametric equations x equals 3 minus 2t, y equals 1 plus 5t, and z equals t. So the point they gave us, I like to call that point P. And then we also need a point on the line, Q, and then we need to connect P to Q. We could use the constants from the parametric equations as a point on the line. Because that's how we set up parametric equations, is with a point on the line and the direction vectors. So what are the constants in those parametric equations? 3, 1, and 0. So that's one way you can do it. Or you can pick any value of t to plug in. You can say, I'm going to let t equals 2 and plug in t equals 2 and see what your x, y, and z are at. And that's another point on the line. Plug in t equals 5. That's another point on the line. All you need is one point on the line. Okay? So 3, 1, 0 is just one of many, many, many points on that line. We just need to connect P to our line somewhere. And then we're going to create the vector PQ. So our Q's minus our P's, that's going to be 3 minus -4, 1 minus 2, 0 minus 1. So we get 7, -1, -1. We're going to cross that with the direction vector for our line. What is the direction vector for our line? -2, 5, 1. Those are the coefficients on our t's. We get our direction numbers, which are the components of our direction vector, from the coefficients of the t's. So the distance formula was the magnitude of PQ crossed with V divided by the magnitude of V. So the next step is PQ crossed V. So this distance has a little bit more work to it because cross product is more work than dot product. I got -1 minus a -5. I got 4i. I got 4i minus 5j plus 33k. Hold on, I'll do that in a second.
No, yeah. Oh, you were just doing that.
I'll do it in a second, yeah, the decimal. Tyler, did I get you stuck somewhere? Okay. Once we have our vector, we just need its magnitude, and that's our numerator. And then in the denominator, we just need the magnitude of the direction vector for the line. So the direction vector for the line was negative 2, 5, 1. Definitely think the points and the planes are easier. That dot product's a whole lot faster to do than the cross product. Especially since that normal vector is already built into the plane. The line takes longer because we've got to create that normal vector with the cross product. And then the answer is a vector, not a scalar. So then we also have to do magnitude to get the scalar, and a lot more work to do. So these notes will be on Moodle. The video will be on Moodle. The test will be on Moodle.
Is this gonna be due that same day?
It'll be due on Tuesday when we come back to class. Yes. You do not need to show up here on Thursday at all.
Do regular university